So let's go ahead and discuss this. So at the beginning of the unit, I showed you a heating curve, and I told you we would come back to this a little later. So looking at this, looking at this heating curve, the big thing that I want you to see or know, the big thing that I want you to see or know in this heating curve is just kind of, basically, we want to focus in on two areas. We want to focus in on what's going on right here as it's transferring from solid ice to liquid, and look at what's happening here where it transfers from a liquid to a gas. So a question they might ask you, or a type of question they might ask you on the exam for this, is which would you predict should be larger for a given substance? Delta H for vaporization or delta H for fusion, and explain why. All right, so delta H for vaporization. But why does it take more energy to go from a liquid to a gas than it does from a solid to a liquid? Okay, so, and we want to stay away from using the word break, but we have to, because when we use the term break, we associate that with a bond, but we have to overcome all intermolecular forces. So going from a liquid to a gas is going to require more energy. That's why this line is actually longer here, or this period is longer here, is because we're having to add more energy to overcome more intermolecular forces. So those connections between the molecules are going to happen more, or take longer to overcome. Whereas going from the solid to the liquid, we're only having to overcome a few of the forces to get it to be enough to where it's still sticky enough to stick together, but it's going to start flowing now rather than holding a rigid structure. All right. So that's really what I wanted you to see here on this one. Heat of fusion. No, heat of vaporization, sorry. I got to make a note on that one. Heat of vaporization, this is heat of fusion. So the heat of vaporization is going to be larger because you have to overcome more forces, intermolecular forces. All right. So just kind of moving into our notes for today. Come on. All right. So this little chart, all I really want you to focus in on this chart is the idea that we have different types of solutions. And you've seen a chart similar to this before. I know I've given you one like this in the past in Chem 1, if not even in physical science way back when. So I'm assuming your other teachers did that if you didn't have me. So let's look at some of these examples. Where's my notes? There it is. All right. So types of solutions. So if we have a gaseous solution where we're mixing a gas solute with a gas solvent, an example of that would be like air or natural gas. if you think about the natural gas that comes into your house, if you have gas at your house, um, if you've ever turned on your stove and it doesn't light, you smell the gas. Or if I open up one of those valves, you smell the gas. Well, that's a mixture of two things. Natural gas by itself does not have an odor. So they inject another gas into it that has an odor so that you can determine that it's on. Might have is if the solution is in liquid form, and the textbook, this is a textbook slide, points out that vodka is an example of a liquid solution where a liquid is dissolved into a liquid. All right. And basically it's alcohol dissolved in water. So, you know, every alcohol has its own proof or percent by volume, and that's how we look at it. But I don't know why they chose vodka, but antifreeze. Okay, so it's not, guys, it's not that it doesn't freeze. The same thing happens with antifreeze. The whole idea of putting antifreeze in our car rather than just water in the radiator is it expands the range for the freezing point and boiling point. Car engines operate at well over 100 degrees Celsius. So if we just used water in there, the water is going to evaporate out of the system, or it's going to be running through steam through the engine. We don't want, but it was new. All right, so moving on. A type of solution that would be a solid form of a solution. We have a solid metal dissolved in another solid metal, like brass, copper, and I don't remember what the other one is. So like alloys, yes. So you can go ahead and put that there. Alloys, also like amalgams, like what they use at dentist office, those metal amalgams. They're a liquid, and they mix a liquid metal with a solid metal, and it hardens in your tooth and all of that. All right. Unless you have a ceramic filling. Well, I have the metal. The white ones are ceramic fillings, and then you have the metal ones are the amalgam fillings. All right. All right. An example of a gas in a liquid would be like carbonated drinks, soft drinks, carbonated water, anything like that. A solid in a liquid would be something like salt water or sugar solution. And then last one, a gas in a solid. Sometimes certain metals are injected with certain gas, like they inject platinum in. They inject platinum with hydrogen. I'm not real sure the application there. Don't know. That's what I just said. I'm not real sure the application there. I'm not. Possibly. I would have to. I'm gonna have to look that one up. I really haven't. I haven't seen this one in my experience. Maybe we will. All right, but we'll have to do an online lab for that. I need to write the. I need to write the PO for that. All right, moving on. So in solutions, these should look familiar to you. Molarity, moles of solute over liters of solution. We've already worked with this year, but we also worked with this last year. This one should be pretty easy for you to do, as well as percent by weight or percent by mass. You take the mass of the solute over mass of solution, multiplied by 100. This is mainly used in medical field. And if you think about it, if you have like contact solution, or a solution for your contacts, if you look at it, it'll say 5% saline solution. What that's telling you is that it's 5% sodium chloride by volume or by mass of water, or mass of the solution. Same thing when you get when they're giving you a IV. the bags that they give you. If you look on there, it'll have the 5%, 10%, whatever's on there. Mole fraction we have interacted with before. I'll talk about this one a little more later, but we've done these before as well. It's moles over total moles of the solution. Remember, if you have something like NaCl, when NaCl dissociates, we actually end up with a sodium and a chlorine, so that's going to double the amount. So we have to pay attention to that. When it's in solution, it's actually, so we might have 1 mole of sodium chloride, but we have 2 moles total, that because we're dealing with a mole of sodium and a mole of chlorine there. And then molality, again, molality actually is not on the AP. And let's look at this real quickly. All right, so this would be an example of molarity, I believe. Yes. All right, so you have 1 mole of sugar in 125 milliliters of solution. Calculate the concentration of units in molarity. So that should be pretty easy to set up, right? Molarity equals moles over liters, right? So it's going to be 1.00 mole over what? 0.125. We have to convert it to liters because it's moles per liter. So what does that give us? All right. So it is 8.00 mole per liter. And one of the things that I'll tell you in this class, rather than writing 8.00 molar, I would rather you write 8.00 moles per liter. Just know that molarity is moles per liter, and that helps us do a lot of things. All right. Now, going the opposite way, you have a 10 molar solution, sugar solution. What volume of the solution do you need to make do you need to have 2 moles of sugar? So we set it up, and I just want to set it up so it'd be 10 molar, which is 10 mole per liter, equals 2.00 mole over X liters, right? So we can solve for that. We do our, and that's actually 1 liter underneath it there. So we do our application, and what do we come up with? I got 0.2 liters, or 200 milliliters. Check my math. No, really, check my math. All right, and then the last one. Consider separate solutions of sodium hydroxide and KCl. So I'm going to go ahead and I'm going to create me a little divider down here because we're going to look at these separately. Consider 2 separate solutions of sodium hydroxide and potassium chloride made by dissolving 100 grams of each in 250 milliliters of solution. So both of them are going to be dissolved in 0.25 liters, right? But what do we need to do to this 100 grams? We need to change it to moles. So how do I convert grams to moles? Divide it by the formula mass. So I have 100 grams of NaOH and I'm just setting up my dimensional analysis there. So formula mass for sodium hydroxide is I'm going to call it 40. All right. And then we set it up the same way for potassium chloride. 100 grams, 1 mole over, I think this one is 74.6. Now, again, when you're doing these calculations, there's no sense in solving for the formula mass, solving for the moles and then putting it in. Just do it all at once when you plug it in. So what's the molarity we get for sodium hydroxide? I got 10. All right. So y'all scared me for a second there. I got 10.5 molar sodium hydroxide. All right, and the next one I got 5.3. 5.36. All right. And again, writing mole per liter or molar, either way is acceptable as your units. I prefer mole per liter because that actually kind of tells us what we have. And it helps us realize that for going the opposite way. All right. So calculations for mass percent. It is pretty straightforward. The big thing to pay attention here, it says mass of solution. So that is the mass of the solute plus the mass of the solvent. So we just need to remember that as we're plugging them in. So what is the percent by mass concentration of glucose in a solution made by dissolving 5.5 grams of glucose in 78.2 grams of water? So on the top of our equation, the mass of the solute, what's being dissolved is the glucose, so we have 5.5 grams. Real quick before I go any further, how do we know that this is the solute? Because it says made by dissolving 5.5 grams of glucose in 78.2 grams of water. And then the other way, remember water is called what as far as solvents? Universal solvent. So most of the time when you see water there, water is going to be the solvent. So glucose dissolved and then the mass of the solution is going to be 5.5 plus 78.2 grams. And then we multiply it by 100 and that gives us 6.57. Yes. All right. Now, something to tell you about percent by mass. Percent by mass doesn't really have a unit other than showing the percent sign. So when I write this, I would say 6.57% glucose by mass. All right. Just make sure you're kind of clear about that. The most important thing is identifying that it's 6.57% glucose. The rest is kind of unimportant. All right. Any questions on this one? All right. Mole fraction. Like I said, we've done this before in the past. We just need to kind of pay attention to it. So a solution of phosphoric acid was made by dissolving 8 grams of phosphoric acid in 100 milliliters of water. Calculate the mole fraction of phosphoric acid. No. Yes. Assume water has a density of 1 gram per milliliter. So this is an important statement. We can't just automatically assume the density of water is 1. We have to pay attention what's the pressure and what's the temperature and all of that, because that's going to change the density of water. But so we're assuming that this one is at standard pressure, so it's going to be 1 gram per liter. Now, to get mole fraction, what do we need to do to these numbers? So we have 8 grams. We need to convert that into moles. So all right, but we also need to find the mole fraction of water too, don't we? So how many grams of water do we have? We have 100 mils, so 100 mils of water is equal to 100 grams. Formula mass of water is 33.
Oh, it's H2O2. Whoops. I always forget the 2.
H2O. All right, not the, okay. So, all right, I got 0.0816 mole. And then I got, what did we get for the second one? All right. So now to set up our mole fraction. So mole fraction is represented by an X. You can see it right here. So it's going to be X H3PO4 equals, so we'll put the moles of H3PO4 on top.
Is that a times? Is that what that means?
No, it's mole fraction. It's this little goofy, I think it's a chi. So, and even though we call this mole fraction, we want the answer in a decimal form, but it's going to be moles of H3PO4 on top, and then on the bottom we have to do the total moles of solution, so it is 0.0816 plus 5.55 on the bottom. So what is our mole fraction? Sure, I got 0.14. It must be what you put in for. It depends on what you put in for your. So if you did 0.082. Huh. It might be a. All right. So as I said before, molality. You from molality, you don't have to do a calculation on the AP, but even if you did, molality is a pretty simple calculation. Moles of solute over kilograms of solvent. But in my Chem 1 class today, I said kilograms of solution, and I had to go back and fix that. So, so they'll get that wrong on the test now, as well as anybody that watches that video. Actually, I put a note in the video. All right. So, just moving forward, formation of a liquid solution. Um, these are just steps into doing this. So we separate the solute into individual components. So if we have sodium chloride being dissolved in water, and I'm going to say dissolved in water. All right. So the first step is we have to separate the solute into its individual components. So what we're really looking at is Na plus and Cl negative. Now, is the water molecule going to separate into hydrogen and oxygen? No, because it's covalently bonded. But what will happen is some of those IMFs that are happening between the water molecules will disperse. So we'll have fewer intermolecular forces in there.
Does that mean there's going to be more free floating?
Well, as the salt ion, you should basically given rooms for the salt ions to come into play. So what'll happen is normally we would have an attachment to, say, a hydrogen off of another water molecule there. But instead, what we'll have is we'll have a sodium ion that comes in between, and then this water molecule may actually kind of flip around then.
So would it happen in terms of gas because
Hmm?
would there be a
No, you're not going to see that. You're just going to see that this ionic solid kind of disassociates and it changes the way the IMFs interact. Because remember, this ion is more attractive than the partial positive side of the water molecule. All right. So allowing it to interact. All right. So, so another way to kind of look at this is in a molecular drawing way. And while we're talking about all of this, I want you to keep the word entropy in mind. Did I spell entropy right? No.
entropy?
I'm just off today. All right. So I want you to keep in mind entropy. Does anybody recall what entropy is?
The tendency to go towards chaos?
All right. Yes, the tendency to go towards chaos or disorder in this case. So if you think about this solid solute, a salt crystal is very ordered, it's very structured. But that's hard to maintain. It's going to require energy. So basically, it's trying to move to its lowest energy state. So what we're going to see here, in order for this to go to this, we have to add energy, right?
Yeah.
So we're going to have energy into the system. Same thing here. In the solute, to overcome those intermolecular forces in this solvent down here, what are we going to have to do? In order to, if we're trying to change the phase of a liquid or kind of separate the liquid, we have to apply heat. So we have to send energy in again. So what I'm wanting you to understand is this delta heat 1 and the delta heat 2 are always going to be positive. Now, the end result when this mixed together, which is delta H3, may be a positive, it may be a negative. That just really depends because it's going to go to its lowest state. So it may be positive, it may be negative, but we're trying to see what our overall transfer of the solution is, or overall change in the solution as it forms. So let me show you this in word form and explain the steps. So when we're doing one of these calculations, step 1 and 2 require energy, since forces must be overcome to expand the solute and solvent. Remember, we have to expand the molecules. We have to either break the ionic bond apart or overcome the intermolecular forces between the solvent. The next step usually releases energy, but it could be a release of energy, and it could be an absorption of energy. It just depends. So the enthalpy of change associated with the formation of the solution is the sum of the delta H values for the steps. So delta H for the solution is equal to delta H of solute plus delta H of the solvent plus the delta H of the solution. So delta H of the solution may have a positive sign or it may have a negative sign because energy could be released or energy could be taken in. Depends on the situation. It depends on what's happening there. And so let's look at it as a graph now. All right, so first glance, these graphs kind of confused me, but as I look at it over a bigger picture, I kind of see it now. So this is our solute and our solvent right here. So we're having to add energy in to expand those molecules. That's not really an important thing. All we're going to look at is energy in this one. All right, so possibly time or something like that. So we have to add energy to expand molecules. And saying molecules there is maybe a little bit of a misnomer, but I think you get what I mean. We're either going to separate the ions or we're going to overcome some intermolecular forces. Now, so we add that energy in, and then we come over here to this line. This line is the heat of the solution. So what we can see is if the overall heat of the solution is this large, what we're going to see is this is going to end up being negative, right? Since both of these are positive, this is negative. I need to go back and change something on the last slide, so we'll come back to that. All right. And then lastly, we look at this last part right here. This is the change for the solution. So because this was such a negative, so much energy out, this becomes a negative charge on this one. So this one would be exothermic. Well, not the top. The overall reaction here is exothermic because more energy went out than went in. Yes, sir.
So if like the negative energy was the same length as the positive energy, would that mean there was no energy release?
Yes, that would have been there was no change. So basically what's going to happen there is it's not going to dissolve. It's just not going to happen.
So it's just like dropping a piece of them more.
Yes, there's no change. All right, so now looking at it from another situation, we have our solute and solvent. We expand them. We have to add energy to it. And then we see over here that we only have this small negative. So this is a positive, this is a negative. But then our overall change ends up being a positive, so that is endothermic. All right, so do y'all see what's kind of going on in this graph as a whole? So all the graph is really doing is comparing the energy in and the energy out, and we're making an overall idea to see if the reaction was exothermic or endothermic as a whole. Not really going to ask you to add up numbers and solve it. Yes, we did. When we did thermochemistry, we kind of addressed this already. It's just a little bit more simplified. And we also did it with reaction rates. Activation energy versus, and that's that one that looks more like, well, more like that, or if it's like that. Now let me back up and correct a mistake while it's fresh on my mind. So let's go back to this. I mistakenly wrote something here. This one, the change in heat for the solution is always going to be negative. Sorry, that was my because we're adding energy here, but this is, if it's going to form a solution, it's always going to make a lower energy state. So it's always going to go to its lowest energy. All right, that was something where I messed up. Now, our delta H for the solution could be positive, could be negative. I got ahead of myself is all I did. So depending on how much energy is exiting here or how much energy is leaving, that can affect this overall answer, making this either a positive or negative. So if these two numbers are greater than this number, it's going to be a positive. If this number is greater than these two, it'll be a negative. All right, that's where I kind of messed up. All right, so we're going to look at this question right now. Explain why water and oil, a long-chain hydrocarbon, do not mix. We already saw this demonstration earlier in class. So in your explanation, be sure to address the delta H, or how delta H plays a role. So we just kind of talked about this. If they're not going to mix, what's the overall delta H going to be? Nothing. Zero. They're going to cancel. So basically, yeah, one's polar. Water is extremely polar, and oil is nonpolar. So they're not going to mix. So the way that I would address this is, one thing I would say, delta H will not show a change. Because solution will not form. Now, that doesn't really answer the overall question. So what we have to do is answer the rest. We need to explain the why it won't mix. So just reading off the statement overall, once separated H2O molecules are more attracted to themselves than to the oil molecules, so mixing will not occur because it is not energetically favorable. Makes sense? All right, in your packet you actually have a copy of the same question. So just disregard the second question, put an X through it, whatever. All right, so kind of summing this up. In general, one factor that favors a process is an increase in the probability of the state when the solute and the solvent are mixed. basically, again, I told you to keep this in mind earlier. This is trying to explain entropy. That tendency to move toward a more disordered state, because disorder takes less energy to maintain than order. You can think about that, even in thinking about that in terms of keeping your room clean. If you want to keep your room clean, you have to be constantly diligent to pick it up. You know, it doesn't take any energy for a house to get messy, because all you do is every time you know, like I have to think in context of my children. Love them to death, but my 13-year-old, he comes home from school, he grabs his snack, and wherever he's sitting is where the trash goes. So that trash will stay there unless either my wife or I expend energy in making the child pick it up by fussing at them or whatever, or we just expend the energy to pick it up and throw it away ourselves. Either way, energy has to be used to maintain order.
Just use your
Um,
telekinesis to throw it away.
yeah, if only I had the force. Um,
Life would be so much easier.
so I just put a note here in between this that the universe favors disorder. All right. So another way to think about this, or another statement to think about this, processes that require large amounts of energy tend not to occur. So oil and water mixing just doesn't occur, because the only way that we can maintain that mixture is if I were constantly adding energy to this, constantly stirring it. So I would have to keep this thing stirring constantly to keep it any degree of mixing in there. So it's just not efficient to do that.
What if you put the magnet in and put it on the hot plate?
But even then, I'm still,
Do you think it would completely like stir?
well, I mean, I can get it to stir, but as soon as I turn it off, what is it going to do? It's going to separate. I don't have any magnet. I don't have any of the stirring magnets out. Wait until I get done with the lecture and we'll see. The coolest one, I think the bullet casing one was. We are going to do a going back to our demo that we did at the beginning of class. Overall, remember that like dissolves like. However, do not write and expect to get credit for like dissolves like on AP. So you need to explain this.
What grades the AP teachers?
Um,
AP gods.
My friend that I get all my notes from.
They pay teachers to
Can you
hold
tell
their
him to give
Her.
me?
Her, it's
Can you
Denise.
tell her to give me 100 and I'll give her $50?
100.
They pay.
I'll
All
give
right.
her $500.
In order for me to apply to be able to do that, I think I have to have been teaching AP for 5 years. But they pay you to go grade them. Plus, you go to like Florida to grade them, so you're at the beach in the
Why
afternoons.
don't they just mail the test to you?
I mean, really, are you going to want to go to?
You won't be at home grading this.
Are you going to want to go to Cincinnati, Ohio, to grade a test, or would you rather go
Yeah,
to
as long as I
Daytona
get,
Beach, Florida?
As long as I get to stay there for a week.
I'd rather go. I'd rather go to Florida.
I get stung by jellyfish every time I go to
All right. So I just got myself dizzy. All right. Explain in terms of energy benefit. So, like I said earlier, I think any time that I'm writing a written response and and you see that it may apply, talk about whether the energy for this was favorable or unfavorable in some way. I think that's what I've gathered from the past couple of units is we need to look at it in terms of, is this reaction going to happen due to the energy available? So This won't mix because it's not energetically favorable. But it does look really, really cool. I would have to find a polar substance that is less dense than the oil. What I could do is if I could find a nonpolar substance that's more dense than water, but I would have to add it before I added that oil, because if I tried to add it with the oil, it's going to dissolve in the oil. Yeah, because like dissolves like, remember? So if I have to add it through the oil, it's going to dissolve in the oil.
Oh, okay. Alright, that makes sense.
Mr. Martin,
Yes.
can I see if I can find a magnet on the station?
No. We will do it in a minute.
Wait, wait.
If you give me... All right. There's something I want to get to, and I just never got there yet. All right. Don't worry about this slide so much. I want to get here. All right. For those of you that took biology, which is everybody, or those of you that are taking biology right now, you might recognize these terms, hydrophobic and hydrophilic.
Yes, I do.
That refers to what part of the cell?
Ooh.
The membrane. The cell
Give me a
wall.
hint and I got it. Give me a hint.
The mitochondria is the powerhouse of the cell.
Give me a hint.
I may be, correct me, but I think it refers to the lipid bilayer.
Which is a part of the membrane.
Yes.
So you could have said yes.
You could have just gave me like that.
All right. So the lipid bilayer, which is in the membrane, which this is what facilitates diffusion, right? Facilitates active and passive transport. All right. So this is where this applies. You have your little membrane, and making up this membrane, you've got these little molecules. All right, and it's been a long time since I've dealt with biology, but
use it every day.
yeah, but I don't pay a close attention. All right, I don't teach biology anymore, so I really don't pay attention to.
You taught biology?
Yes, I did.
Did you like it?
I do
I
not.
didn't like it.
The thing with biology, I was really good at it,
Ooh, I'm
but
not
that's
that
because
good.
I really like understanding why words mean what they mean and looking at word parts to make the meaning.
See, I thought I liked the
So,
math, but
so I was really good at that, but I'm not. So when we have in this bilayer, in this membrane, we have a hydrophobic side and a hydrophilic side. So which side of these molecules, the internal part or the external part, is going to be hydrophilic, which is water loving?
the inside.
Probably the inside.
The inside.
Outside.
I don't know.
I think it's the outside.
I mean,
All right, so
I thought it was because they didn't want to keep water on the inside, right?
well,
I said water level.
you want to keep
Yeah, so the water one's on the inside.
you want to keep a balance. You want to keep a balance of the water on the inside and the outside of the cell, because our cells, if we don't have enough water on the inside of it, what happens to it?
We die.
Mr. Mon, I wasn't taught enough.
They get hypertonic, and they kind of shrivel up.
Is that when you get
If they pull too much water in, they get hypotonic, and they swell and they burst. All right. So that's the hydrophilic part. This is the phobic part.
Are you sure?
Yes. Because basically what we need to happen is we don't want the water to stay in the middle of the layer. We want the water to either stay here or here. So on the inside or the outside.
The stops it from going out or
So
out the way it
so water's going to go through, and it's going to pass all the way through, because as soon as it gets on the inside, now it's kind of scared of these tails because it's hydrophobic.
What keeps it from getting pushed out the way it came in?
Well, that's what keeps it balanced. That's what keeps it in equilibrium. So if too much is trying to go in, it's going to push back out the same way it came in. If it's not enough on the inside, it's going to allow it through.
I got you now.
That's a brave and Mr. Martin conversation. Just leave it alone.
it lets it. That's active transport.
This is
Passive,
this is
yeah,
facility.
that's all I said. If it's equal, yeah, it's going to stay there. That's what I said in a different terms.
Oh yeah, he's always
So yeah, you're right. High to low. It's only going to pass,
going backwards.
but but yeah. But if this area is high and just assume that something did go in there, it's going to go right back out because it's not going to go into the high. It's going to stay in the low. Because this side of the molecule likes the water, so it is attracted to it, but it's not. No, you're right. You're right. I told you it's been a very long time since I taught biology. So anyway, moving on. All right. So here's one of my bads, and I should have taught you this in Chem 1. Henry's law. I did not teach you this term, but Henry's law applies to gases in a liquid. Henry's law and pressure, I guess really pressure really doesn't affect solids or liquids that much, but pressure really affects a gas. So if we're looking at these three containers, we have this gas over the surface of a liquid. As I increase the pressure in the container, what is the gas going to do? More of it's going to go in the liquid. So if you think about like our Coke can, Coke cans are pressurized. Immediately when you pop the top or open up the lid, it makes the little noise and the gas escapes. So as soon as that pressure is released, what starts happening to the liquid itself, or what do you notice? Well, when you're looking at a bottle and you open up the bottle, what does it do? It fizzes, right? It foams. All right. So it fizzes and foams because the gases that were trapped inside the liquid are now able to release. All right. I mean, there is air in between there, but I don't think it's anything to do with dissolved oxygen or anything like that. All right.
So what if I keep doing this? Am I gonna get arthritis?
No. No. If you're going to get arthritis, you're going to get arthritis because you're genetically predisposed to get arthritis. All right. Or you have some sort of immune